Okay, we're going to look at the final exam review day 2 packet that I made. Notably, we want to complete each of these without a calculator because you will not have a calculator on the final exam. Sometimes we'll get answers that don't turn into integers or simplifiable fractions, so we might have to provide exact answers sometimes. So right off the bat, we have a logarithmic equation. We want to isolate the log. Subtract 4, we get 2 log base 3. 2x minus 3 is equal to 8. Divide by 2 on both sides, and we get log base 3, 2x minus 3 equal to 4. I'm going to change forms here to exponential. 3 to the 4th equals 2x minus 3. 3 to the 4th is 81, is 2x minus 3. Add 3 to both sides. I get 84 is 2x. X is equal to 42. Okay, I double check real quick. If I put in 42 here, I would get 84 minus 3, 81. Log base 3 of 81 is 4. 2 times 4 is 8 plus 4 is 12. So it checks, and I don't hit any sort of domain issues. Like, I want to make sure that when I put in a value for x, that the argument inside the log is positive and not 0. Okay, second question, we're given an exponential equation. We might need to use logarithms to solve it. Start by isolating the base being raised to a power. So I'm going to divide both sides by 4. Give me 1/2 to the negative x plus 2 is equal to 8. At this point, I could go ahead and take the log of both sides, but I'm going to choose something a little different. So I'm going to rewrite 1/2 as 2 to the negative 1. And then that's going to be raised to the negative x plus 2. 8 I'm going to rewrite as 2 to the 3rd power. Using my power to a power, I can rewrite the left side as 2 to the positive x minus 2, and my right side is 2 to the 3rd. And then if 2 to something, 2 to the x minus 2, is equal to 2 to something else, 3, well then it must follow that x minus 2 is 3, and x has to equal 5. Okay, quickly go back and check. So if I look at my original problem, if I plug in 5 here, I would get 1/2 to the negative 3, which is like 8 times 4, which gives me 32, so it checks out. I could have, at this stage, I could have chosen to do log base 1/2 of 8 equals negative x plus 2. I could have then done change of base, could have done log 8 over log, and let's make it log base 2 of 8 over log base 2 of 1/2 equals negative x plus 3. Log base 2 of 8 would have been 3. Log base 2 of 1/2 would be over negative 1 equals negative x plus 2. Get negative 3 equals negative x plus 2. Negative 5 equals negative x. X is equal to 5. So we get the same thing either way here. If you use logarithms, I like the idea of changing the base because I notice that there's a commonality between 1/2 and 8. They are both powers of 2, and that allowed me to do it my way. Okay, speaking of changing bases with commonalities, we want to look at number 3 here, where that's exactly what we're going to have to do. So we have this piece of the equation, 1 over 25 to the 2x minus 3 times 5 to the 5x minus 375 over 3 to the 3 minus x. Okay. Now this problem is only going to be possible without a calculator if the numbers are really set up in such a way that we have like 125, 1 over 25, 5. 375 divided by 3 is actually going to be 125. Okay. And so we actually have powers of 3 as each of our bases. Or sorry, powers of 5. So our first one is 5 to the negative 2 to the 2x minus 3. Second one is just 5 to the 1st to the 5x. And the third one is 125 is 5 cubed to the 3 minus x equals 0. I can apply my power property of exponents, so I can end up with 5 to the negative 4x plus 6 times 5 to the 5x minus 5 to the 9 minus 3x equals 0. Then I can use my product rule of exponents, And so I can add these two exponents because we are multiplying by the same bases here. So I get 5, -4 and 5 gives me just x plus 6 minus 5. I'm going to rewrite it as -3x plus 9 equals 0. Now at this point, our properties of exponents don't usually work over subtraction or addition. You might try to factor something out of everything, but there's actually a much more straightforward method here. So instead of doing any of that, I'm actually just going to add 5 to the -3x plus 9 to both sides. And so we get 5 to the x plus 6 equals 5 to the -3x plus 9. Now I have 5 to some power, x plus 6 is equivalent to 5 to some other power, -3x plus 9. So that must mean that x plus 6 is equal to -3x plus 9. Add 3x to both sides, subtract 6 from both sides, I get 4x is 3. X is equal to 3 over 4. Now this is not going to be particularly easy to check. Suppose if we plug in 3/4 to our first term, 2 times 3/4 would give us 3/2. Yeah, so we're not really going to have a great time trying to check this one. We can go back through our math and look at it and make sure that it looks good. If we really wanted to check it, we probably could pull it off. But I'm just not going to, and I'm going to hope that's right. Okay. And then problem number 4 here, we have a change of base situation. We have log base 4 of x plus 3 plus log base 1/4 of x minus 4 equals 3 log base 64 of 6. So what we notice is all the bases, well, they're powers of 2, but even better, they're powers of 4. Okay, so if I could get all the bases to be the same, I would be pretty happy. Now my method for doing this is kind of just to straight up change everything. So I have log base 4 of x plus 3. To get from 1/4 to 4, I would need to raise it to the -1 power. So I'm going to raise the inside to the -1, which is giving me plus log base 4 of 1 over x minus 4. Alternatively, you could use change of base, which would look something like log base 4 of x minus 4 over log base 4 of 1/4. Then you would say log base 4 of x minus 4 over -1. And then we can use our power rule to bring that up there, or something else with that -1. I just kind of like my method, so I'm just going to stick with that. Equal to. I'm going to use my power property of logs, bring that 3 up, so log base 64 of 6 cubed. Okay. And then to get from 64 to 4, so that these bases all match, I would need to take the cube root. So I'm going to cube root 64, cube root the inside, and so I'm going to get log base 4 of x plus 3 plus log base 4 of 1 over x minus 4 equals log base 4. Cube root of 6 cubed is just 6. Okay. All right. Now I'm going to use my rule where if I'm adding two logarithms, I can multiply their insides, product rule of logarithms. So I can say log base 4 of x plus 3 times 1 over x minus 4, which is the same thing as x plus 3 over x minus 4. Oops. Equals log base 4 of 6. Now if log base 4 of all this equals log base 4 of all this, well then the insides must be equivalent, so I could just say x plus 3 over x minus 4 equals 6. Multiply both sides by x minus 4. Okay. Subtract x, add 24, I get 27 equals 5x, x equals 27 over 5. Now I want to check against my domain. 27 over 5 would be 25 over 5 and then 2 over 5. So I think that would be about 5.4 as a decimal. If I go and substitute that back in for x, I get positive values in my argument of the logs, so everything is all good. And I would assume that that works. Okay, so that is a little bit of exponents and logarithms. It's a little review of how they work. Being able to change the bases is a really key skill, both if you need to look at the matching bases of the exponential equations, or if you want to look at the bases of a logarithmic equation. Being able to get everything to match and then use our properties is really important. Next section, we're going to look at inverses. So we're going to find the inverse of each function. Starting off here, we have g of x is equal to some square root function. If we imagine this on a graph, okay, we have negative and then the square root of x minus 3 plus 4. So our vertex would actually be at positive 3 comma 4, right? And we have a negative square root function, so we're going something like this, and we're going off. Let's make that a different color. Okay, so that is going to maybe help us when we go to take the inverse, because the inverse of a square root function is a quadratic. But we only want half the quadratic because the square root only sort of matches half the quadratic. So the process for finding the inverse is relatively straightforward. We say y equals all this and then switch x and y. Square root of y minus 3 plus 4. And then we solve for y. So x minus 4 equals negative 2 square root of y minus 3. Divide by negative 2. X minus 4 over negative 2. A little awkward to write that in the denominator. I'll leave it for a second. I'm actually just going to go ahead and pull that out in front. Negative x minus 4 over 2. Then we're going to square both sides. Square and square. Because this was a negative out in front and we're squaring the term, we can kind of turn it back to positive. So we actually end up with x minus 4 over 2 squared. Suppose you could leave the negative, doesn't do any harm, equals y minus 3. Add 3 to both sides, and we are done. So we get negative x minus 4 over 2. Write that a little neater. Negative x minus 4 over 2. And note that this negative is not with the x, it is with the entire expression. Squared plus 3 is equal to g inverse x. However, this describes a full parabola. The vertex of that parabola would be at 4 comma 3. So that would be somewhere like here, 4 comma 3. However, we're currently describing all of this. We only want half of that because we had the square root function that only matches half of that. Because our square root function was negative, that's going to tell me I want the left half of the parabola. Okay, so I want the minus side of my parabola. So I need to restrict my domain. I need to get rid of the right half of my parabola. And so I'm going to say for my final answer that x has to be less than or equal to 4, the x-coordinate of the vertex. Okay, and so we would say this and we'd be all done. Alternatively, the inside here might look slightly different. You could have ignored this negative because we're squaring it, so it'll be the same as making it positive, but that's the idea. Okay, in our second example, number 6, we're given a function that is to an even power, a power of 4. Normally that would produce maybe a graph that somewhat looks like a parabola. However, we have this domains restriction, which allows us to invert the function. Because if we tried to invert it right now, we would get this. Failing vertical line test, not a function. So we restrict our domain of the initial function to x is less than or equal to 5. Right from here, 5 is the x-coordinate of the vertex. So I actually only want this part of the parabola so that when I invert it, maybe I get something that looks like this. Okay, algebraically, we do the same thing though. We're just going to switch x and y. So x equals 1/2 x minus 5 to the 4th power plus 1. Subtract 1 from both sides, multiply by 2. said switch x and y, but that wasn't x, y minus 5. Okay, so now we would want to take the fourth root of both sides. Maybe we distribute that 2 in. So we'll do 2x minus 2. When you take an even root, remember, like that even power makes it so whether this is positive or negative, we get the same result. So you're supposed to take the plus or minus fourth root of both sides. However, because of our domain restriction, because we only want the left half of our parabola, which corresponds to the negative root. The positive root would be up here. The negative root has to be the left half of the parabola. So when I actually do my root, I'm going to say negative fourth root 2x minus 2 equals y minus 5. Okay, add 5 to both sides. Negative fourth root of 2x minus 2 plus 5 is equal to, and now I should use proper notation, f inverse x. And we are good. And I don't need a domain restriction on this because I've already kind of restricted it by going from plus or minus to just minus. So by having that negative root at the end, I've already kind of covered the domain and function, vertical line test, all that stuff is already taken care of. Okay. Number 7. So we take a look at number 7. We have h of x is equal to some exponential function. Inverse of an exponential function, right? Exponential functions look something. We have a vertical asymptote, or sorry, horizontal asymptote. Maybe we look something like this. Then our logarithmic function, the inverse of that, we're going to have a vertical asymptote and look something like this. So algebraically, we do the same thing to start. We switch x and y. So we say x equals 2 times 3 to the power of y minus 2 plus 5. Going to work to isolate the exponential piece. So I'll do x minus 5 divide by 2 is equal to 3 to the power of y minus 2. I need to get my variable of y out of the exponent, so I'm going to need to use logarithms. I'm going to say log base 3 of x minus 5 over 2 is equal to y minus 2. Okay, using our conversion between exponential and logarithmic form, or you could say we are taking log base 3 of both sides, however you like to think about it. Coming over here, we get log base 3 of x minus 5 over 2 plus 2 equals y, or at this point, I'm going to put back in h inverse x for proper notation. And for exponents and logs, all the domain and range and all that is already taken care of just implicitly, and we're good. One little quick check for inverse functions also is the inside becomes the outside and the outside becomes the inside. So that can be a decent way to make sure you're right, and I'll show you what I mean by this. So if I have x minus 3 on the inside, I should get x plus 3 on the outside of my inverse. If I have x plus 4 on the outside, I should get x minus 4 on the inside. So that checks out. Then if I have negative 2 division by or multiplication by negative 2, should have division by negative 2, which I essentially have here. So I am able to say, okay, that looks pretty good. I must be right. If we look at the second example, I have plus 1 outside, so I should have minus 1 inside. Interestingly, I have 2x minus 2 inside, but recall that that could be written as 2x minus 1, and so now I can see that I have minus 1 inside. Then there's 1/2 outside. It's like dividing by 2. There's multiplying by 2 inside. My first example, the 2x minus 2, is just with that distributed. Then we have minus 5 inside the function, turns into plus 5 outside the function, and then this domain restriction makes the negative out here. So this is how you can sort of quickly check your inverses to make sure they're correct. And same thing with the exponential. Plus 5 was outside, minus 5 is inside. It's got to be the opposite. So instead of outside, it's inside. Instead of plus, it's minus. Times 2 was outside, so that means divided by 2 is going to be inside. Minus 2 was inside. plus 2 is outside. And so we check it and we look good. Okay, how many more? We got 2 more inverses. So we have a log function here. Let's use a nice color, light blue. So first thing here, right, this is going to follow the same idea as the graph up here. So let's switch x and y and solve. So x equals 2 log base 3 of y minus 1 plus 4. Subtract 4 from both sides. X minus 4 is 2 log base 3 of y minus 1. Divide by 2. X minus 4 over 2 equals log base 3 y minus 1. I like to change forms. You can raise, or like sometimes you could say, oh, I'm taking 3 and I'm raising both sides to that, canceling this, and then I get my thing. I personally just like to change forms or think of it that way. Either way, you're going to end up with 3 to the power of x minus 4 over 2 is equal to y minus 1. Add 1 to both sides, we get 3 to the x minus 4 over 2 plus 1 is equal to y. Great. And instead of y, I should use j inverse x, proper notation at the end. Okay. Nothing else to worry about. Domain and range take care of themselves for these ones. Let me just check my answer. So I have minus 1 inside, plus 1 outside, plus 4 outside, minus 4 inside, times 2 outside, divide by 2 inside. Okay, log had a base of 3. My exponential has a base of 3. Everything checks out. Confident that this is right. Last problem here, k of x is equal to x plus 1 squared divided by 2 plus 5. Use another cool color, sort of a lavender purple. This time x is greater than or equal to -1, so my domain restriction. So I have an even power function. It's just, this time it's a quadratic, a parabola. So normally they look something like this. When we take their inverse, that would imply it would look something like this. However, that's not a function. It fails the vertical line test. So we turn it into the plus or minus version, and we restrict the domain of the original such that it can be inverted. So I'm actually going to only focus on this part of the function. Okay, algebraically, we're going to do the same thing. So we'll say y is equal to, switch x and y, x equals y plus 1 squared over 2 plus 5, x minus 5 equals y plus 1 squared over 2. Multiply by 2, I get 2 times x minus 5, or 2x minus 10 equals y plus 1 over 2. Now, again, because we have something that's being squared and we're taking the square root of it, we got to recognize that if that thing were positive or negative, when we square it, it turns positive. So I need to take the plus or minus root 2x minus 10 is equal to y plus 1. But based on my domain restriction, greater than or equal to -1, that's the x-coordinate of the vertex. That's the positive half of my parabola, which corresponds with the positive square root. Negative square root's down here. We don't want that. So we're only taking the positive root. So when we come over here, we'll take positive square root 2x minus 10 minus 1 is equal to y, or in this case, k inverse x. I don't need to add any domain restrictions because I just did that. I only took this positive part. That takes care of my domain problems or range problems or whatever, and we're happy. We should check. So if I look at this, I have kx plus 1 inside. I have minus 1 outside. I have plus 5 outside, which looks like we have minus 10, but if I factor out that 2, it's actually minus 5 inside. So that's good. Divide by 2 outside times 2 inside, and then square becomes square root. Since it's greater than, we take the positive root. Everything checks out, and I'm confident in my inverse here. Okay. All right, continuing on here. In this problem, we are given a logarithmic function f of x, and we know that f of -20 equals 2. We are given the domain of f of x is -∞, -12. Determine a possible equation of f inverse x. Okay, so we have to think about what do we know about logarithmic functions. So I'm going to draw a little graph. Generally, if we have some parent logarithmic function, let's just call it log base 2 of x, by default we have an asymptote at x equals 0. We would go through the point 1 comma 0, and look something like this. So if our domain is now negative infinity to negative 12, that's telling me that, let's pretend this is negative 12 here. That's telling me that we're actually going this way, okay? So somehow our graph has to be reflected in sort of over that x-axis or in that sort of dimension. Now, one way to do this is if I had some function, we'll just call it y equals log base 2 of x. Well, if I wanted to reflect over the y-axis, I could say y equals log base 2 of negative x, because now all the same things are occurring. They're just occurring on the other half. When I put in negatives, negative negative turns it positive. So that's going to get me to the opposite sort of domain, where I go from negative infinity to my asymptote instead of from my asymptote to positive infinity. However, I also have to stop at negative 12, not at 0. So that means when I plug in negative 12, I should get 0, okay? Because 0 is the cutoff point. We can't have negatives in logs. We can have positives. We cannot have 0. So at that point when we get 0, that's our sort of cutoff where our asymptote is. So if I plug in negative 12, for example, right here, well, that's going to turn into positive 12, right? Y equals log base 2 of 12. But if I want to get 0 in there, well, I should have a minus 12. So that means up here, I should have negative x minus 12 inside my log. When I plug in negative 12 here, I get negative 12, positive 12, minus 12. I end up with log base 2 of 0, giving me undefined, giving me my asymptote. So because there's no, well, actually there is one other criteria. F of negative 20 is equal to 2. So there's different ways we could accomplish this. I'm just going to say, why don't we use the point. So we get out 2 when we put in negative 20. Okay. So I can say 2 equals log base 2. Negative 20 is positive 20. Minus 12 is 8. So it turns out picking log base 2 is actually really convenient because this evaluates. So 2 equals 3. Log base 2 of 8 is 3. But 2 is obviously not 3. I would need to either multiply times 2/3. So I could put a 2/3 out in front here. Or maybe it's more natural to think about, oh, it's just minus 1. So if I put a minus 1, well, we're good. So that means f of x could be equal to log base 2 of negative x minus 12. Let's see, minus 1. The problem is asking us to determine a possible equation of f inverse x. So let's find the inverse of that. Switch x and y, so I would get x equals log base 2, negative y minus 12, minus 1. X plus 1 equals log base 2 of negative y minus 12. And exponentiating, I get 2 to the x plus 1 equals negative y minus 12. Add 2 to both sides, or sorry, add 12 to both sides. 2 to the x plus 1 plus 12 equals negative y. Divide by negative 1 and I get negative 2 to the x plus 1 minus 12 equals f inverse x. And note that I can take this as my inverse function. There are many, probably infinitely many possible answers. Okay, but that's one of them, and that's how I would personally go about solving this. If this instead in here had been like a 9, maybe I would have picked a log base 3. If it was 25, maybe I'd pick log base 5. So we kind of have to hope that that comes to some integer power. Kind of got lucky with log base 2. I should confirm this. So if I plug in 2 to my inverse function, I should get out -20, because an inverse function takes what were the outputs of the original function and gives back the inputs that created that output. So if I want to check, okay, I could say -2 to the 2 plus 1 minus 12 should equal -20. So -2 to the third minus 12 equals -20. -8 minus 12 equals -20. And so that checks out. -20 equals -20, which is great. So that means my function appears to work. It appears to invert and change the inputs from outputs back to outputs to inputs. And that's sort of a line of thinking that would get us through that. Okay. Let's try that for next one, number 11. So it says, given an exponential function where g of 5 equals -106, and the range of g of x is -infinity to 10, determine a possible equation of g inverse x. So we know g of x is exponential. Okay. Now our parent exponential, let's assume, let's try 2 to the x, y equals 2 to the x, has a horizontal asymptote at y equals 0, and goes up from that 0 to infinity. Because our range of this function, g of x, is -infinity to 10, well, that tells me that I actually have a horizontal asymptote at 10, and I go down to -infinity. So maybe I look like this, okay? Maybe I look something like this. I don't really know. But a reflection over the x-axis in this case, and then a shift up would accomplish this. So if I begin with some parent function, say g of x equals 2 to the x, and then I consider my range, so I say g of x equals 2 to the x, and I'm going to throw a plus 10, and that's going to put my asymptote right there. But at the moment, 2 to the x would look something like this. So I need a flip. I'm going to make it negative. So I'm going to say g of x equals -2 to the x plus 10. So we raise 2 to some power of x, and then we just take that result and make it negative. And that probably takes care of what we need it to take care of. That's going to give us the general shape and the range that we want. So now we need to just make sure that our function g of x goes through the 0.5 and -106. So let's plug that in and see what we're working with. So -106 is equal to -2 to the 5th plus 10. Okay, 2 to the 5th is 32. So I get -106 is equal to -32 plus 10. Now we can kind of see that that is pretty clearly not the case. If we want this to be true, we're going to need to either multiply by some factor out in front or add something to shift us left or right. I'm going to go ahead and say, let's pick an a value. So let's pretend there's an a value out in front. So times 2 to the 5th, or -a times 32, or 32a. So if I do that, and then I subtract 10 from both sides, I'm going to get -116 equals -32a. Okay, so if I want to solve for a, I divide both sides by 32. Negative divided by negative gives me 116 over 32 is a. Both are even, so I could say 58 over 16 is A. Still even, we could do, let's see, 29 over 8 is equal to A. And, okay, now I'm assuming I actually messed up. When I made this problem, I probably wanted this to be minus 10, because then that would make A equal to 3 and things would come out nicer. But it's fine that it doesn't. We can work with the fractions. So if that's all said and done, I end up with g of x should be equal to negative 29 over 8 times 2 to the x plus 10. That is not the only possibility, but that appears to be one possibility that works. If I plug in 5 here, well, this becomes 32. 32 divided by 8 would give me 4. 4 times 29 gives me 116. Or negative 116. And then add 10 to that, and I get the negative 106 that I want. So my answer definitely works. It meets the criteria. I still have a horizontal asymptote at 10. I still go down, giving me a range of negative infinity. So this function works. And again, there are infinitely many functions. Maybe there's a different base that would work better. But this is the one I picked and it works. However, that's g of x. We want g inverse x. So we're going to flip x and y. So we're going to say x equals negative 29 over 8 times 2 to the x plus 10. X minus 10 equals negative 29 over 8 times 2 to the power of x. I'm going to multiply by the reciprocal to divide away that a value. So I'm going to end up with 8 over 29, negative 8 over 29, x minus 10 equals 2. I seem to have a habit of doing that. 2 to the y. I'm supposed to switch x and y. 2 to the y, 2 to the y. Okay, now I need to take the log base 2, switch to log form, log base 2 of negative 8 29ths, x minus 10 is equal to y, or in this case, g inverse x. Okay, and so this is actually my answer for g inverse x. Should probably check that. So if we check, we could say log base 2, negative 8 over 29. For x, I should plug in what was my output, right? We're trying to take a inverse function that takes our outputs and returns the original input for our original function. I also need parentheses in here. So negative 8 29ths times negative 106 plus 10 with the log base 2 is supposed to be equal to 5. Looks a little messy, but let's go for it. So negative 8 29, negative 106 plus 10 is going to give me negative 96. It's supposed to equal 5. Now, how are we going to do 96, 29, and 8? I guess there's no great way to do it. 9 times 8 is 72, so 8 times 90 is 720. 6 times 8 is 48, so we're going to get 768 over 29. Do we think that's going to reduce? I have no idea. Well, let's hope. So log base 2 of 768 over 29 is going to be equal to 5. Presumably that's supposed to be telling me that that 29 divided by that should be 32. Which honestly I'm a hair skeptical of. Oh wait, it's not plus 10, it's minus 10. Okay, that makes life a lot easier. My apologies. So this is minus 10 in here. But one thing I want you to note, like I'm going to leave that mistake in here because it is important to be sort of evaluating your work as you go, and something wasn't looking right to me. And so I went back and I was able to retrace and look back. I was like, I looked over here for a second and looked here and I was like, oh wait, it's not a minus, it's a plus. So like mistakes just happen. You gotta be constantly evaluating your answers and be like, does that look reasonable? Does that look right? Does that look reasonable? As you go, and that'll allow you to catch more mistakes and then find out how you can fix them. So this is -8. This is -106 minus 10, which is -116 equals 5. Okay, that's going to be good because 29 times 4 does give us 116. So if we divide that, we get 4. So we get log base 2 of -8 times -4 equals 5. Then we get log base 2 of 32 equals 5. 5 equals 5. So it checks out. Our logarithm does in fact work. Okay, hopefully that's instructive. Get to watch me and how I make mistakes, but kind of monitor for those mistakes. Not that I always catch them by any means, I certainly don't. But that's one thing you should be doing as you do your math, is just constantly evaluate, like, does this look right? Does this look right? And that'll help you sort of catch things and sort of build your general mathematical knowledge. Okay, next one, number 12. Given a fourth root function, f of x equals all this, write an exponential function g of x such that g inverse x goes through the vertex of s inverse x. All right, delightful. A lot of things happening here. So we want the vertex of f inverse x. Well, right off the bat, if I want the vertex of f of x, right, I want to know what makes my inside 0, which is going to be positive 2/3. So I'm going to say 2/3. And then when that's 0, all this becomes 0, leaving me with just 4. So a vertex of f of x is 4. Well, that actually means the vertex of f inverse x is going to be 4, 2/3, because the inverse function takes all your x, y's and switches them to y, x, or interchanges those points. Now I need to write an exponential function such that its inverse goes through this. So the inverse of an exponential is a log function. So I'm actually just going to write the log function and then I'll invert it. So I need a log function that goes through 4, 2/3. This is actually super easy to do. You can pick anything you want. I find log base 2 is super easy to work with. So I'm just going to say y equals log base 2 of x to start. And I'm supposed to plug in 4. Hang on a second. That's not exactly what we want to do. I need to write an exponential function so that g inverse x goes through the vertex of... Oh yeah, no, we're good. Don't listen to me. Doing too much math in a row. Okay, so when I plug in 4 here, sorry, log base 2 of 4, I'm supposed to get out 2/3. But obviously log base 2 of 4 is just 2, so I would get y equals 2. But I'm supposed to be getting 2/3 in place of y. 2/3, 2/3, 2/3. 2/3 obviously isn't 2, but it's not that far off. I could multiply 2 by something to get 2/3, or I could add something to 2 to get 2/3. Although honestly, in this case, multiplying seems easier. So why don't I just multiply it by 1/3? 1/3 of 2, 2/3. So if I had 1/3 all along, then I would have gotten 2/3. So if my function was g inverse x equals 1/3 log base 2 of x, well, that meets the criteria. This function g inverse x goes through the vertex of f inverse x, right? When I plug in 4 here, I get out 2/3 here, and we're happy. My instructions were to write g of x, though. So now I need to take g inverse x and invert it to get g of x. So I'll go through that algebra. So I can say x equals 1/3 log base 2 of y, multiply by 3. 3x equals log base 2 of y. Switch forms, and I get 2 to the 3x equals y, but y really is f of x. And voila. And I can double check with another check. I can check this. Put parentheses here. So if I plug in 2/3 to this, 2 times 3 to the 2 to the 3 times 2/3, I get 2 squared equals 4. So I plug in 2/3, get out 4. Meaning in my inverse function, so f of 2/3 equals 4, that means f inverse of 4 is going to equal 2/3, which we built the function to confirm, but I'm just double checking. And we're good. Again, many, infinitely many solutions. This is the one I found. Okay, moving right along here. So we've been talking exponential and log functions. Let's recall, why do these have asymptotes? So why does an exponential function have a horizontal asymptote? And so the reason for that is if we think about our base, right, and our exponent sort of represents repeated multiplication of our base. And there's a criteria, b has to be a positive number, so greater than 0, and it can't be 1. That's sort of implied in our exponential functions. But as long as that's the case, for example, if I had b is 2, so it's repeated multiplication of like 2 times 2 times 2 times 2 times 2 times 2, right? If I keep doing that, you'll notice I'll never be negative. Never negative, right? That would be 2 to the first, or 2 squared, 2 cubed, 2 to the 4. We just keep getting bigger, or too many multiplications of 2. Okay, well, what about this? 2 to the 0 is 1. Notice that's not negative. What about 2 to the negative 1? A half. And then 2 to the negative 2 is like 1 over 2 times 1 over 2, which is a fourth. Notice that's not negative. 2 to the negative 10 is a half times a half times a half. No matter how many times we times by a half or multiply by a half, we're still not negative. Okay? So we're going to get a horizontal asymptote because we can get really small. And by small, I mean close to 0. But we're never going to get negative. I can keep plugging in more and more and more negative exponents and get closer and closer and closer to 0, but I never get there. So that's why we have a horizontal asymptote. Okay? We can get really small, but not quite 0. The asymptote just ends up being this k value, because this part of the function is going to get really small. Small will get small. And then we just add on this. We add on that after. So that gets our asymptote. So our horizontal asymptote is just going to be y equals k. Why does it have the horizontal asymptote? We can't multiply or divide by a positive number and get a negative number. We can get really close to 0, but never quite there. Okay. Why does a logarithmic function have a vertical asymptote? Well, on the one hand, you could just say, if you have some exponential function, right, which looks like this, and we have, as we have more and more positive x values, we go off to infinity, and then as we get negative x values, we get really close to 0 in our asymptote. Well, our log function is just a reflection over the line y equals x. That's sort of how inverses are defined. If you define a log as the inverse of an exponential, if we consider the line y equals x here, if we draw in some exponential function like this, like this, and then maybe we draw in our log function, logically they should look maybe like that. I don't know that that's how they actually look, but that's the general idea. One will have a vertical, one will have a horizontal asymptote. You should probably think of a better explanation, such as like the log represents the power. Let's just write this. Log represents the power you would have to raise the base to get the result, but in our case, because it's a function, we're talking about this. So I'm going to say result. I'm talking about the inside of the function, the input, okay? But the problem is I can't ever raise a power, just like we said for exponential, can't raise base to power and get 0 or negatives. And again, implied in this base is that the base is greater than 0 or the base does not equal 1. So it's the same exact explanation, basically, just a little bit reversed. We can't, like, raise that base to some power and get a negative, or we can't raise that base to some power and get 0. So it's undefined for that input of 0. So it switches our inputs and outputs. So our equation to the asymptote this time is going to be what makes that inside 0. So if x minus h is 0, well, that would imply x equals h. So x equals h is the equation of our asymptote. Whatever we plug in to this function, if we put in h, we get 0. If we put in something, like if I put in x is greater than h, then I get some output, and I'm happy. If I put in x is less than h, oops. If I put in x is less than h, and then I subtract that, well, I'm going to get a negative. That's no good. Very sad. And if I put in x equals h, I get 0. And so that's not happy. Whew. All right. Number 15. Given the function f of x equals 2 times 3 to the x plus 2 plus 5, identify p of x, the parent function of f of x. Great. So parent function is just going to be p of x equals 3 to the power of x. It's the most basic function that shares the features. This adds a vertical shift up, this adds a horizontal shift left, and this adds a stretch factor of 2. Okay. Well, I should have written that down. Okay, so shift up 5 units. Okay, shift left 2 units. Vertical stretch by factor of 2. So those are the transformations that map p of x to f of x. Now for an interesting question. Rewrite it in an equivalent form that does not have a horizontal shift. How can we get rid of that h value? In our h value here, we're talking about that 2, right? Exponential function, the h is that part that shifts you left and right. So I can get rid of that. I can bump it out. So if I do 2 times 3 to the x plus 2 plus 5. Well, using our property of exponents here, I could rewrite this as 2 times 3 to the x times 3 squared. And that's our property of exponents that says if I have 3 to the x times 3 squared, that's equal to 3 to the x plus 2. That pink kind of looks horrendous. And then I can write my multiplication in any order, so I can say 2 times 3 squared times 3 to the x plus 5. And then I can just turn that into 2 times 3 times 3, which is 18, times 3 to the x plus 5. So that's basically what we should do. I'm just going to put f of x equals 18 times 3 to the x plus 5. And we're good. So it's kind of interesting. A horizontal shift in an exponential function can be accounted for instead by some vertical stretch or shrink. So instead of saying, oh, we just shifted our function left, we could actually say, no, we stretched it again by a factor of 9. And that's kind of interesting and has to do with our properties of exponents and multiplication and so on. All right, we got some inequalities. Many inequalities are best treated as equations, and then sometimes you have to test points, then test points or think. Now, I like to think when that's an option. It actually ends up being a little easier. But in our case here, maybe we'll test points. I don't know. So let's go ahead and treat it as an equation. So if I say 2 absolute value of x plus 3 equals 12x minus 4, I'm already starting to solve. Absolute value of x plus 3 equals, divide by 2, 6x minus 2. Now I can consider my positive and negative case. Positive case would be x plus 3 equals 6x minus 2. Solving that, I would get 5x equals 1 and x equals 1/5. Okay. Does that sound right? 5x, x equals 1. There it is again, monitoring my answer, taking a quick peek, didn't look right. So x equals 1 is actually the solution there. On the other side, we take the negative case, so x plus 3 equals negative 6x plus 2. 7x is going to equal negative 1, so x equals negative 1/7. Okay, again, that looks a little odd, negative 1/7. No, but that checks out. Okay, I'm going to go for the think method here. So rather than sort of saying, oh, those are my points, let me test between, I'm going to think. If I were to plug 1 back into this equation, 1, 1, 2 times 4 is 8, 12 times 1 is 12, minus 4 is 8. So that just checks out. So that's good. So I'm just actually testing the point. Negative 1/7 though. So if I do that back in here, negative 1/7, I'm going to get something positive on this side. Negative 1/7. So that's going to make this negative. Minus 4 is also negative. So I'm going to get the 2 absolute value of something equals a negative. Well, that's not possible because positive 2 times the absolute value is always positive, right? And getting a negative doesn't work. So this is extraneous. And I didn't even fully plug that in and test the point. I just went for that little thinking method. Okay. Extraneous. But you could plug it in and solve, and you'll see it doesn't work anyways. Am I going to be able to erase these? No. Let's go for a little tap erasing. Tap, 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 tap. Wahoo. All right, so that's not going to work. Extraneous. Great. However, okay, so that's extraneous. And now that tells me this is my one place. So if I go back and I think again, here's my function 2x, absolute value of x plus 3 equals 12x minus 4. In a sense, that's saying my absolute value, when is absolute value going to equal, this is some linear function. When is that going to be the case? Specifically, when is it going to be greater than or equal to? Okay, and we said it only intersects in one point. So if I overlay this and I put it on my absolute value, so here's my absolute value v representing this. Here's my linear line representing this. And it intersects at this point x equals 1. Okay, x equals 1. And that is actually going to be, I don't know, maybe right here. It's going to be hard to draw. Okay, awfully steep slope, too steep. It's like 1,000,000 degrees in here where I'm recording this. So sorry if I'm losing it. All right, so that intersects at this point, x equals 1. That's the only place it actually intersects, 1 comma something. And I put my vertex, I know that this x negative 3 would be the coordinate of the vertex. So negative 3 comma something. So if I know it works there, and I want to know where is my function, the absolute value, greater than? Well, if I look at this, it's clearly less than right here. Less clear, but still obvious as it's greater than here. So it's actually x is less than or equal to 1 is going to be my solution by thinking. Now, if that seems a little wild to you, plot a number line. We can just test it. So we can say, here's 1. Here's some numbers to the left of 1. Here's some numbers to the right of 1. Say I pick a number such as 0, okay? And I plug it in here, and I plug it in here. You know what? Let's do it down here. 2 absolute value of 0 plus 3 greater than or equal to 12 absolute, or times 0 minus 4. 2 absolute 3 greater than or equal to negative 4. That's true. Okay, so this works. So I want this piece of the solution. And I'm happy. So that is less than or equal to 1, which we said. If I test a point here, like say I try 2, and I do, let's say, 2, absolute value of 2 plus 3 greater than or equal to 12 times 2 minus 4, getting a little squished. 2 times 6, 12, greater than or equal to 12 times 2 is 24 minus 2. That's false. So this doesn't work. So I don't want values of x greater than 1. So if you sort of imagine your regions and solve it, it'll reveal it also. Or you can do the thinking, whatever sounds better to you. Okay. All right. That one was a pretty tricky example. This one's more realistic. Number 17. So here we have negative some quadratic less than or equal to negative 10. Now I'm going to think right away. Quadratics make parabolas. Negative quadratics make negative parabolas, like this. Then the line y equals negative 10 could be imagined as some constant. So if I want, when we are less than that constant, I want this part and this part. So if I treat this as an equal sign and find these 2 points, I can say it's less than or equal to this side, greater than or equal to this side, and we're happy. So let's go for it. We are going to solve this equation. Pretend it's an equal sign. First, we're going to distribute out. So we get negative x squared plus 7x plus 12 plus 2 equals negative 10. So we need to contain everything into a single quadratic. Hopefully it factors. Otherwise, we're completing the square quadratic formula. Negative x squared minus 7x minus 12 plus 2 gives us plus 10 equals negative 10. Add in another 10. Negative x squared minus 7x plus 20 equals 0. Quadratics we said equal to 0. Now we want to know, does it factor? Pull out that negative sign. We don't need that. Negative x squared plus 7x minus 20 equals 0. You did need to distribute it here. Whoop, right? Or that's actually not the right place. You needed to distribute it here because this needed to combine with this and this. So you did need to distribute that negative sign, even though we factor it out later. Now, does something add to 7 and multiply to negative 20? Boy, do I hope so. Let's see. 4 and 5 would be nice. Doesn't appear to work. Actually, I didn't even take my own advice. Whoops. So we're supposed to distribute that negative sign in, meaning this would be negative 10, because that would be negative 12 plus 2 is negative 10, meaning when we add 10 to both sides, we get plus 0, which is nothing. Factor out the negative. Now it definitely factors. So we get negative x plus 7 equals 0. Zero product property tells us x equals 0, x equals negative 7. Okay. Well, now that I've already thought about it, negative 7 then would have to be this one. X equals 0 would have to be this one. And because I've thought about what my shape looks like and done the pre-thinking, I can confidently say right now x is less than equal to negative 7 or greater than equal to 0. That's just straight up my answer. If I hadn't done that thinking and I only knew how to test points, sure, cut this off. Try again. So I could say, if I draw my number line, let's do a different color. Roasting. Should have turned on the AC. So here's my 0 point that we flagged. Here's negative 7, and I have 3 regions to test. So I want to pick easy numbers. Let's pick 1 from here. Let's pick negative 1 from here. Let's pick negative 10 from here. So if we go through and we test each of these, let's We can test them in our original equation. We can test them wherever. But say I do negative 10 plus 4, negative 10 plus 3, plus 2, less than or equal negative 10. I'm expecting this to be true. Negative, that's negative 6, that's negative 7, plus 2, less than or equal negative 10. Negative positive 42, so negative 40 less than or equal negative 10. True. So this works, so I can go this way. Okay, that's all good. Now I'll test negative 1. So if I went back and did this with negative 1 instead and plugged it in, we'd find something else. Probably need a little more room on the paper for this. So let's see, negative 1 plus 4. We're expecting this to be false based on our reasoning earlier. Less than or equal negative 10. Negative 3, 2 plus 2 less than or equal negative 10. Okay, negative 6 plus 2 less than or equal negative 10. Negative 4 less than or equal negative 10. False. Okay, so we don't want all of this. And then last but not least, we'll plug in 1 plus 4, 1 plus 3, plus 2, less than or equal negative 10. So if we're doing this negative, this turns into 5, 4, plus 2, negative 20 plus 2. Man, I hope this is useful for somebody. And that's true. Okay, so this part of our thing works. So I want x is less than or equal negative 7, x is greater than or equal to 0. Boom, our thinking was valid, and we're happy. Run a little low on space here. Let's draw a little line, cut that off there. Yahoo. Alrighty, let's go number 18. We have a log function greater than or equal to 1. If we visualize the graph of our logs typically have some sort of horizontal asymptote. So in this case, it's going to be at negative 7. And then maybe it looks a little something like this. And if we think about 1 as being some constant function, we want to know when is this greater than or equal to that. So there's not too much else going on here. So our algebra should sort of just yield the answer, but we'll still test points and see what happens. So let's go 3 log base 2 of x plus 7 minus 1 equals 1. Replace this with an equal sign. We would end up with log base 2 of x plus 7. Add 1 gives us 2. Divide by 3 is 2/3. Then we get 2 to the 2/3. Fix that. Equals x plus 7. And 2 to the 2/3 minus 7 is equal to x. Okay, based on our graph, it looks like if that's our point, right, that's the x value we just found, we're probably just going to be above that, right? So we could probably just say anything to the right, and we can just say x is greater than or equal to 2 to the 2/3 minus 7. Now 2 to the 2/3, 2 squared is 4, and then to the 3rd root, so we could say it's cube root of 4 minus 7, or negative 7, oops, plus cube root of 4. It's another way of writing that. Let's do the test though. So if I imagine that point, so here's 0, negative 7 plus cube root of 4. So that's pretty close to negative 7, right? Say that's negative 7 plus, all right, it's 2 to the 2/3 here. If I want to go to the right of that, why don't I just test 0? So I could say 3 log base 2 of 0. Oops. 0 plus 7. You know what? That's not even going to be that nice. Let's try 1. Let's test this point here. So 1 plus 7 minus 1 greater than or equal to 1. Is that true? Well, 3 log base 2 of 8 minus 1 is greater than or equal to 1. It's 3 times 3 minus 1 greater than 1. 9 minus 1, 8. Okay, so that's true. So that means this works. Everything to the right of here should be true. meaning that our inequality was correct. Should I test something to the left? Probably. So what's less than negative 7 plus 2 2/3? Easy one that's going to work out pretty nice would be negative 9. 3 log base 2 of negative 9 plus 7 minus 1 greater than or equal to 1. 3 log base 2 of negative 2 minus 1. 3 times a half. Log base 2 of negative 2 is... Oh, wait, no, it's undefined. My bad. So undefined greater than or equal to 1. Well, that's not true. Undefined is not greater than 1 equal to 1. It's undefined. So this is all false. This we wouldn't want. So we'd be good, done, and happy. All right, moving on to number 19, we have the absolute value of x squared minus 4 is less than 4. So let's think about what this looks like. If we draw a little graph here, okay, think about is, where is x squared minus 4? If we look at that, we would say that's the same as x squared, just shifted down 4. So our function would look a little something like this. However, we're taking the absolute value of it. And the absolute value takes negative, makes positive. So all this negative piece down here is actually going to end up reflecting and becoming the positive version. Okay, so that's the first thing we want to recognize, is our graph actually looks a little something like this. Okay, now let's go ahead and solve this. The algebra should still work, because we want to know when is this function less than 4. So maybe 4 is here, maybe it's here, maybe it's here. So we're not exactly sure where that's going to be, but that's the general gist of things. So first of all, I'm going to split this into my positive and negative case. Okay, I'll say x squared minus 4 equals 4, or x squared minus 4 equals negative 4. X squared is going to equal 8, or x squared is going to equal 0. Well, this is pretty easy. This one's going to x equals 0 is going to be my solution. Here, x is going to equal plus or minus the square root of 8. Okay, now simplifying the square root of 8, we would say x equals plus or minus 2 square root 2. So if we think about this logically, x equals 0 is on the y-axis. And because our vertex we would have expected to be on the y-axis for this x squared minus 4, that should now be this point right here. Meaning that if I take my function, if I want to know when is it less than this line, this should be x equals 0, right? 0, 4. This should be when x is positive 2 root 2, and this should be when x is negative 2 root 2. If I want to know when I'm less than that, that's going to be from here and here, and not including the points. So I should be able to say just right now that x, or I'm going to use interval notation. So I'm going to say from negative 2 root 2, not inclusive, to 4, not inclusive, and then from 4 to positive 2 root 2. Except instead of 4, I for some reason was saying the y-coordinate, that should be the x-coordinate, to 0 and 0. Okay, so that's my solution. A little differently, I could say x is between these values, 0, and x is between 0 and 2 root 2. Okay, now if I wanted to test this on a number line, okay, here's my 0 point, here's my 2 square root 2, here's negative 2 square root 2, so that would give you 1, 2, 3, 4 regions to test. So we could do that. If I want to know is x squared minus 4 less than 4, I can plug in values from each region. So if I do 1 squared minus 4 less than 4, well, that's negative 3 less than 4, false. Oh wait, no, true. That is true. Okay, so this region here is true, because I just tested negative 1. Now let me test this region with a 1. So I'm going to say 1 Oops. I'm sorry, this video's struggling a bit. 1 squared minus 4 is less than 4. 1 minus 4 is less than 4. Negative 3 is less than 4. So we get the same thing. That's also true. Okay. Then something more than 2 root 2, I can test whatever I want. I mean, I know 5 should be more than 2 root 2, right? So I could do 5 squared minus 4 is less than 4. Pretty easy to see that's false, right? So I don't want this. False. Compared to earlier, we were true. And we can test one last point if we would like. We can test like maybe negative 5. So negative 5 squared minus 4. We're going to get the same thing because our graph has that symmetry. So we get 21 is less than 4, also false. So that's false. So we can see the true range, or the true regions, whoops, are here and here. So we capture that in our original answer. All right, last couple of problems here. So here we're just simplifying radicals. You can prime factor these, and that should be good. So we could say 9 times 5, 3 times 3. So I'm able to pull out 3. I get negative 6 square root 5. Right? Minus, this factors to 5, 4, 2, 2. 6 factors to 2 and 3, neither of which will pair out. So here I get negative 6 root 5, then minus 2 root 6. Okay, combining our like radicals, negative 6 roots 5 minus 6 more roots of 5 gives me negative 12 square roots of 5 minus 2 square roots of 6. That's as far as we can go. Okay. Next example, we want the nth root of 3 times 2 to the n times x to 2n times y to the n plus 3. So you could think about this a number of ways. If we think about it more algebraically, we have this times 2 to the n times x squared to the n times y to the n times y cubed. And then if we look at all these parts individually, the nth root of 3, the nth root of 2 to the n, nth root of x squared to the n, nth root of y to the n, nth root of y cubed, we can see that the nth root of 2 to the n would be 2, nth root of x squared is to the n is x squared, and the nth root of y to the n is y. So those parts will simplify, and I'll get out a 2, I will get out a x squared, and I will get out a y, with the parts remaining in the root, our nth root of 3y cubed is my final solution. Determine the root 3 expression with a coefficient of 1 that simplifies to the following. All this is basically saying is our final answer should have root 3 of something, and that's what's supposed to simplify to this. Okay, so if that's true, we basically just have to cube each of these and put them back in the root. So I'm going to say 2 cubed, right? Cube root of 2 cubed, cube root of m cubed, cube root of n to the 6th. All of that is equivalent to this part right here. And then I still have the cube root of 5mn squared. And then with our properties of radicals, we can combine all this under a single radical because it's the same degree. So we get 2 cubed times 5, m to the 4th, because of m to the 1st, m cubed, and n to the 8th. And so this all simplifies back to our original thing, but the point was to have an expression that would simplify back to it. What was the original expression? So 2 cubed is 8 times 5 is 40, and then m to the 4th, m to the 8th, and we are done. Last problem here, solve for C. Notice how these are getting a little easier. So first thing, we want C terms on one side. Because we've got all these terms with C in them, but we can't really combine them because there's too many other variables included in the terms. So I'm going to subtract C from both sides. I'm going to subtract B from both sides. Okay. we're going to get 3ac minus 6bc minus c equals a. Okay, now we can factor out c. This is our little trick here. Out comes c, and so you get c, 3a minus 6b minus 1 equals a. And then divide away everything and we get c equals a over 3a minus 6b minus 1. And we're done, okay? Okay, so I hope this video was helpful. And yeah, keep up the good studying.